We are beginning chapter 4, and so this initial lecture is simply an introduction to chemical bonding in general. So the first and probably most important thing to understand is what is a chemical bond. A lot of people tend to think, okay, there's literally some type of physical connection between atoms. No, a chemical bond is an electrostatic attraction. It's an attractive force, okay? And when I say electrostatic, what do we mean by electrostatic? It just means that there's some charge development. So you'll see as we go through bonding that there's some type of bonding that takes place between fully charged ions and other bonding, covalent bonding, which takes place between neutral atoms that perhaps are polarized. You'll see what I mean as we get there. But anyway, every single chemical bond is a result of an electrostatic attraction between the atoms that are bonding. And one way to kind of visualize this, and I am not going to have you do calculation, this is Coulomb's law, but I do want you to understand the ramifications that Coulomb's law has to chemical bonding. So look at the variables. These are the variables that affect the strength of an electrostatic attraction, okay? Q is the charge on the particle undergoing the attraction. And so if we're talking about ions, fully developed charge, if let's say the cation had a charge of +1 and maybe the anion had a charge of -2, okay, so that's literally the values we'd put in for Q. D is the distance between the atoms that are bonding or attracted to each other. So let's look at what type of relationship these have. The size of the charge is directly related to the attraction. The charge is directly proportional or related to attraction, right? So the higher the charge, the stronger the attraction, and you'll learn the stronger the bond. On the other hand, distance is inversely related, okay? Distance between atoms is inversely related to attraction. That makes sense, right? So the farther two atoms are from each other, the less attraction they're going to feel. And we'll talk about the factors that would increase or decrease this distance D. All right, I have mentioned previously, but it's worth emphasizing again, that it is the valence electrons in atoms that participate in chemical bonding. So what are the valence electrons? Those are electrons in the highest energy level. And if you envision a Bohr model, okay, like we have right here, the electrons in the highest energy level, so that'd be the red ones, are farthest away from the nucleus, okay, and therefore they feel less attraction for the nucleus, and it's easier to remove them or manipulate them. And so that's why the valence electrons are what participate in chemical bonding. Now, as we talk about the different types of chemical bonding, there are some bonds, which we'll go into more detail, that share their valence electrons with each other. And we'll go more into detail, but that is covalent bonding. You may remember that from high school. And there are some chemical bonds that form by one atom completely transferring some or all of its valence electrons to another atom. And that results in ions and what we call ionic bonds. Just as a reminder, again, we've touched on this before, but it's very important, especially in the bonding unit, that you remember how many valence electrons atoms have. And so the number of valence electrons that the A groups have is predicted based on the group number that the atom is in. So group 1A all have 1 valence, group 2A have 2, and etc. Okay? Helium's an exception here, but the rest of them in group 8A have 8 valence. Now, another thing I'm going to remind you of is that 8 electrons is considered a full outer shell. Okay, it is very stable, and so I've kind of made the pun before that all atoms are noble gas wannabes. In other words, you will notice that in most chemical reactions, the atoms that do not have a full outer shell, that's everything but the noble gases, right, will react in a chemical equation to get them to have a full outer shell, or 8 valence electrons. And that'll help you understand a lot of chemical bonding too. All right, we have talked very briefly, or introduced very briefly, about covalent and ionic bonds. And this, I like this table just because it's kind of compare and contrast. But you will see, we'll go in more detail about all of them. But ionic bonds are formed between metals and a metal and a nonmetal. And covalent bonds are formed between 2 nonmetals. Occasionally a metalloid will participate. And we won't talk much about it, but there's something called a metallic bond, and it just happens like pure copper, for example. The atoms of copper, we say they form metallic bonds with each other, and we'll talk about that a bit more. And each of the type of bonds helps determine the properties that the resultant compound has, okay? So one thing that's very important to know is that, like, this is probably sodium chloride, right? Is that the properties of a compound are completely unrelated to the individual atoms or elements that make that compound, okay? Once a compound is made, it has totally new properties. However, the type of bonding, whether it be ionic, covalent, or metallic, does help determine the type of properties that the compound has. Just a little bit more compare and contrast of the different types of bonding. So you will learn in an ionic bond, what you end up with are individual ions that are very strongly attracted to each other because the fully developed charge. So think back to Coulomb's law on the first slide of this PowerPoint. But so you don't have individual, quote, molecules of, let's say, sodium chloride. You have a big conglomerate, a big three-dimensional conglomerate of ions that are massively attracted to each other. And that's why most ionic compounds are crystalline solids, because there's such tight packing between them. Now, covalent bonding, the atoms are not quite as tightly packed together. They're not quite as strongly attracted to each other. There are not ions, there aren't fully developed charges. There are partial charges, which we'll talk about. But because you don't have as strong of that Coulomb electrostatic attraction, covalently bonded materials can be gas, liquid, or solid. Okay, they're not as predictable as ionic compounds. And finally, just a word about metallic bonding. Metals to the left of the stair step, we've talked about them having low ionization energy, which means it doesn't take much energy to remove the valence electron from a metal, right? That's why metals tend to give up their electrons to become cations in a chemical reaction. And because the electrons in metals are so easily or so loosely held, when a metal just exists by itself, all of the electrons in all of the metal atoms tend to just kind of associate with each other. We call it a sea of electrons. They all kind of float to the surface and associate with each other. There's some level of attraction there between the electrons and all the nuclei of the different metal atoms. Alrighty, a little bit of bonding theory, and this is a type of graph that it's important for you to understand, to either be able to sketch or interpret. So they are a potential energy diagram, which anytime you see a potential energy graph or diagram, that is usually drawn to let you know where the most stable position is for whatever you're talking about. So remember, in nature, the lower the energy, the more stable, right? So a negative energy is a good thing in nature, okay? That means it's stable. And really, anything that's going to happen spontaneously in nature is because by doing so, the system goes to a lower potential energy. So let's pretend that these blue spheres are hydrogen atoms. And let's say in the beginning here, they aren't close enough to feel each other. So we're going to call that zero energy, okay? Then we're going to start bringing them closer to each other. And so that's what the x-axis is. It's internuclear distance. And don't worry about the units. That's picometers, but don't worry. The internuclear distance is the distance between the two atoms. And so as that internuclear distance decreases, in other words, as they get closer together, look what happens to the potential energy of the system. It's going down. It's getting more stable. Okay? And that is simply because of the electrostatic attraction between the electrons. So each hydrogen atom has one electron, right? And so the electrostatic attraction that's going on in this covalent type bonding is between the electron of an atom with the nucleus of the other atom. Okay? That's what the stability, that's what's lowering the potential energy. Now, if the two atoms that are bonding get too close together, the electrons, the valence electrons, will start repelling each other, and that'll become the more important force. That'll become more important than the attraction. So they can become too close, and then the stability goes away and energy starts increasing. That's not good. So why, in addition to understanding bonding better, what else can we get from a potential energy diagram of a bond forming? Well, we can actually determine or see what the bond length and bond energy is, the strength of which the attraction is. But when we say bond energy, that's what we mean, the strength of the attraction. And how do we do that? Well, the first thing you need to be able to do is find the lowest point, the most stable point. And then if you drop down from that to the x-axis, that will tell you the bond length. That's the most optimum bond length for potential energy, the lowest possible potential energy. If, again, you, from that lowest point, you go over to the y-axis, you can get the bond energy, and that's the strength with which the two atoms are attracted to each other. So that's important to know, and that would be a typical type question I might ask you. So here's a sample one for you to test your understanding of what I just went over. Look at this graph and tell me what the bond strength and the bond length is. If you think you can do it, go ahead and shut off the video and then turn it back on. I'll tell you. So here I go. I'm going to start giving the answer now. So here is the lowest energy point. When I drop it down, okay, this is not a very precise scale, so I can kind of estimate. I'm going to estimate that that's 3.7. This A with a little circle over it stands for angstroms. Don't worry about that so much right now. Alrighty, so bond energy, you go over to the y-axis, and my estimate is that the bond energy would be minus 100. Okay, so that's pretty simple. And here it is, just in a little bit neater form than me scratching it. Alrighty, so now we're going to talk about the potential energy diagram for ionic versus covalent bonds. So again, an ionic bond involves two ions, and that's because one of them has completely transferred its valence electrons to the other one. And you can probably predict or see which one has done which, right? Because cations, what have they done? They have given up their valence electrons, right? And that's why they're a cation, positively charged. Anions have gained an extra electron. That's how they have the negative charge, and they're an anion. So ionic bond is between a cation and an anion. Same thing, okay? They start approaching each other. Potential energy goes down. Very similar, not any significant difference except the distance, the bond length, and the bond energy, okay? But a similar type of thing. So covalent bond has two neutral atoms that approach each other rather than fully developed ions, but it is still an electrostatic attraction, again, between the valence electrons of one of the atoms and the nucleus of the other. All right, so again, same thing. You can predict the bond length and the bond strength by looking at these. Let's talk in a little bit more detail about the formation of an ionic bond. So metals have low ionization energy. We just went over that in the periodic trends, right? Low ionization energy, which means it's easier to remove electrons. Okay, it takes less energy. And so the metals will tend to be the donors. They will tend to donate valence electrons and become a cation when making an ionic bond. Okay, nonmetals to the right of the stair step have higher ionization energy, which simply means that valence electrons are more tightly held to the nucleus, and so it requires more energy to remove them. So nonmetals in general do not tend to become cations. They tend to prefer to accept electrons from metals or other electron donating substances to become anions. Okay, and so you can see by pairing certain metals up with other nonmetals, it's like a marriage made in heaven. So look at potassium, for example. It's in group 1A, okay, which means it has one valence electron. And so by donating its one valence electron and then getting a charge of +1, its new outer shell is now full, okay? And similar things going on with chloride. Chlorine is a halogen in group 7A. It has 7 valence electrons to begin with. It only needs one more to have a full outer shell. That is 8 electrons. So it is going to want to gain 1 electron. So again, elements from group 1A combine with elements from group 7A in a 1-to-1 ratio, okay? And you can see here, match made in heaven. Now, as ions, they each have a full outer shell and a very strong attraction between the two ions. They have made an ionic bond. When talking about ionic compounds, we often mention lattice energy. Lattice energy is the strength, okay, with which ions are held together. And it's all based on Coulomb's law. And this is important to understand, okay? Just kind of heads up. This is a real common multiple choice type question. So I'm going to just kind of write an abbreviation of Coulomb's law. So the energy of attraction is proportional, okay, to the charge on ion 1 times the charge on ion 2 divided by the distance between them, okay? So just as a reminder, as the charge of the ion increases, of either one of them increases, the strength of the attraction also increases. Remember, directly proportional to charge. So let's look at this table for lattice energies, okay, the strength with which the ions are held together. And let's look at, and remember, a negative, you expect a negative energy. Like all these are negative because remember that's stable. That's indicating the system is stable. It's at a low energy, below zero, which is no attraction. All right, so magnesium chloride in this table has the highest lattice energy. And it's a little bit more than twice as high as lithium fluoride. Why would that be? Well, let's look at the charges, right? So lithium is from group 1A, so when it loses its one valence electron, gets a charge of +1. Fluorine is from group 7A, so when those elements, the halogens, become ions, they have a charge of -1. Let's compare that to magnesium chloride. Magnesium is in group 2A, so when it becomes an ion, it has a charge of +2. Chlorine, we're still dealing with chlorine here, so it's from group 7A, just like fluorine is. So when it becomes an ion, it has a charge of -1. Now, listen to me really carefully in case you're daydreaming. However many of the ion there are, in this case there are 2 chlorine, makes no difference, okay? All that matters is the overall charge on an individual ion, okay? So I don't care if you have 2 of them, 1 of them, 5 of them, 10 of them. It doesn't change the lattice energy. All right, so now you can simply see when you multiply 2 times 1, you're gonna get 2 as your overall charge. When you multiply 1 times 1, you're gonna get 1 as your overall charge. So look at that. It about doubles the lattice energy, magnesium chloride versus lithium fluoride. One more thing that I want to point out here. Let's see if I can erase all this. Now, we talked about the charge, and that is the most important factor in determining lattice energy, is the charge of each of the ions. But what about distance? Okay, we wrote Coulomb's law, and we also said that distance is inversely proportional, right? So let's kind of verify that. So here again is the energy of attraction. All right, and it's proportional to charge, and it's inversely proportional to distance. So that means as distance gets larger, the energy of attraction, or the lattice energy, should get smaller. So let's compare lithium fluoride to lithium chloride, okay? They each have the same overall charge, okay? They both have lithium, which is +1, right? Fluorine, halogen, becomes -1. Chlorine is also a halogen, becomes -1. So there's no difference in the charges of the individual ions. So something has to be making the lattice energy of lithium chloride lower. Not lower. I hate it when it's negative because then you don't know how to say. Lattice energy, say lithium chloride has actually a weaker. Okay, I'm gonna have to be careful my wording on the test. Lithium chloride has weaker lattice energy, less negative. Why? Okay, we know it's not the charge, so it has got to be the distance. So now I'd like you to look at a periodic table, and we're gonna compare lithium fluoride to lithium chloride. So they both have the lithium cation, and lithium, if you look at the periodic table, it's pretty far up there, right under hydrogen. So it's pretty small, right? So if you remember your periodic trends, as you go toward the top of a group, it's pretty small. So those are a wash, that's no effect. However, let's compare the size of fluorine to chlorine. So look at your periodic table. Chlorine is farther down in the halogens. It is significantly larger, primarily because it has one extra energy level than fluorine, right? So now, what is going to be the relative distance between lithium and chlorine and lithium and fluorine? All right, so the thing to write down is the larger the ion or ions, okay, the greater the distance between them, okay, the greater D is, okay, so D is larger for large ions, so that means large ions have weaker attraction, okay, so let me write that down too. So larger ions have weaker attraction. So now let me just imagine that, I'm sure everyone's gone through this, right? It's easier to hug somebody tightly to you if they're around your size, right? Or smaller. I'm sure we've all, well, maybe not all of us, but most of us have probably had the experience of trying to hug somebody a whole lot larger than us. And we just can't get quite as close. We can't wrap our arms all the way around. That's just kind of a way to visualize what's going on, okay? Let's look in a little bit more detail with covalent bonds. So covalent bonds form between two nonmetals. Now, why would that be? Let's talk about what a covalent bond is first. Covalent bond is when two atoms share their valence electrons, right? So there are no ions, no charges involved. So it's just basically two atoms will come together. So let's think about two oxygen atoms. Oxygen is in group 6A, which means it has 6 valence electrons. So if you have, and remember, every element's a noble gas wannabe, so they all want 8 valence electrons. So each oxygen wants 2 additional valence electrons, right? Well, by coming together and sharing, look what ends up. Okay, we end up, if they each share 2 electrons, okay, that's a covalent bond. It happens to be a double bond because there are 2 pairs in there. But by sharing valence electrons, guess what? They each have now 8 valence electrons, or they each feel like they have 8 valence electrons, okay? Whoops, I wrote that wrong. So they each can call claim to the 4 in the middle. Now we'll see more about, there are several different types of covalent bonds, and we'll talk more about that when we get into Lewis structures. But basically, if 2 atoms share 1 pair of electrons, okay, that is called a single bond. If, as in oxygen, they share 2 pairs of electrons, it's a double bond, and 3 pairs of electrons shared is a triple bond. And then we'll also talk about nonpolar and polar bonds. So, still on covalent bonds now. Remember I said that even though a covalent bond does not have ions, does not have fully developed charge, they still have what we call partial charges, okay? And the partial charge that an atom feels in a compound depends on its electronegativity. All right, so what is electronegativity? Electronegativity, okay. Electronegativity is the attraction an atom has for extra electrons. Okay, attraction for extra electrons. Somewhat vaguely related to electron affinity, but still significantly different. Electron affinity is energy to actually take on an extra electron. This is just the level of attraction for extra electrons. So electronegativity, it's important to keep in mind, if you look at the periodic table, that electronegativity increases going towards the fluorine atom. The fluorine atom is the most electronegative atom on the entire periodic table. So the closer another element is to fluorine, the higher its electronegativity or attraction for other extra electrons is. All right, so if we have a chemical bond that involves two identical atoms, so molecular chlorine, okay, obviously each of the chlorines has the same electronegativity, so they each have equal attraction to extra electrons. So when you talk about a chlorine bond, it's a single bond, which means it involves one electron pair, and that shared electron pair that makes up the covalent bond is shared equally, okay? So we're going to say shared equally. And when we have covalent bonds that are shared equally, we call it a nonpolar covalent bond. Now let's look at a covalent bond that has different elements involved. So let's say HCl. HCl still has a single bond between the hydrogen and chlorine atom, which means they share two valence electrons between them. However, they do not share equally because hydrogen and chlorine have vastly different electronegativities. So if you think about the periodic table, chlorine is someplace here. Oh, by the way, I meant to mention the noble gases have zero electronegativity, no attraction for extra electrons. They don't need them. So anyway, chlorine is below fluorine. And where is hydrogen? Okay, hydrogen's way over here. So hydrogen has quite a low electronegativity, and chlorine has a much higher electronegativity. Well, what does that mean? That means that chlorine is going to hog the shared electrons. So if you look at this color diagram, what it's showing you is that these shared electrons are going to spend more time in closer to chlorine than they will hydrogen, just because there's a stronger pull for them by chlorine. So when electrons are shared unequally, but it's still a covalent bond, it is called a polar covalent bond. And we say that the more electronegative atom has a partial negative charge, and the less electronegative atom has a partial positive charge. Now, when the electronegativity difference is huge, okay, when the electronegativity difference is huge, okay, when there's a real big gap between electronegativity. For example, when you're talking about a metal, okay, metals have very, very low electronegativity. And when they are coupled with atoms that have a very high electronegativity, so when the difference is large, what you're going to end up with is an ionic bond. And what's going to happen is the electronegative atom is going to pull on the valence electrons from the sodium so hard that it's actually going to steal them, take them away, so that you end up with individual ions. Still held very close together by electrostatic attraction, but ions nonetheless. All right, so this is a really cool table of electronegativities. And again, as I said, fluorine is the most electronegative element on the entire table. Notice that no noble gases are shown because they have electronegativity of 0. But just an easy way to remember is the closer you get to fluorine, the higher the electronegativity is. Now, we can roughly predict the type of bond that's made by subtracting the electronegativity of the elements that are involved in making a bond. All right? So, for example, let's say that I didn't already know that two chlorine atoms or two of any of the same atoms will make a nonpolar covalent bond. Let's say I just didn't know that. And I wanted to use this little rule where you take the absolute difference in electronegativity, which I'm going to abbreviate like that, difference in electronegativity. Now, the difference is an absolute value. Don't worry about pluses and minus. Just take large minus small. So each chlorine has electronegativity of 3. All right, well, the difference in electronegativity of any diatomic molecule where the atoms are the same is 0. What does that mean? Well, the rule of thumb is when the difference in electronegativity is less than or equal to 0.4, we call it a nonpolar covalent bond, which means the valence electrons are shared equally. Okay, valence electrons are shared equally for nonpolar. Students get polar and nonpolar mixed up, so make a note of that. All right, so now let's look at something that has 2 different elements and is not shared equally. Let's look at carbon monoxide. Okay, see what type of bond it is. So the electronegativity for carbon monoxide, okay, so let's see, carbon is 2.5 and oxygen is 3.5. So I'm just going to do 3.5 minus 2.5. Remember, it's an absolute, the absolute value. Okay, so the difference in electronegativity between carbon and oxygen is exactly 1. What does that mean? The rule of thumb says if the electronegativity difference between 2 atoms that are bonding is greater than 0.4 but less than 2, and that's what carbon monoxide would be, it is polar covalent bond, which means the valence electrons are still shared, but they're shared unequally, okay? Now, if you're dealing with a polar covalent bond, you need to be able to assign partial charges. So there's no reason you would know there's a triple bond. I just do, so I'm writing it in. Okay. So if I asked you to write out the partial charges on carbon monoxide, remember you would put the partial negative charge over the more electronegative atom, and that would be oxygen, right? Oxygen's closer to fluorine. And the partial positive charge over the less electronegative atom. And what that tells you then is the oxygen atom is hogging. These shared electrons are spending more time closer to oxygen. And that's it for the introduction to chemical bonding.